video, we're going to introduce the concept of a limit. So limits are going to be fundamental to most everything we do in calculus. Understanding limits is going to be extremely important. So a limit can be evaluated in one of three ways. We can evaluate a limit graphically, numerically, or algebraically. We're going to focus on numerical and graphical evaluation in this video. So let's start by defining a limit. So we are going to have a formal definition of what the term limit means, but there's also a more intuitive way to think about what the term limit means, and I want to look at that first. So let's think via an example. So I want you to imagine crossing a room in two different ways. Number one, imagine crossing 1 foot at a time. And number two, I want you to imagine also crossing the room by cutting the distance by half repetitively. So what I mean by that is imagine starting at one wall, and each time you travel across the room, you're cutting your distance from one wall to the next by half of what it originally was. So crossing 1 foot at a time, or using a set measurement and then crossing the distance by cutting it, or crossing the room by cutting the distance by half each time. So let's look at a picture of what this might look like. So imagine this is a room. You're starting at one side and crossing over to the other side, or vice versa. It doesn't matter which way we're going. So let's just say we're going from left to right. So let's imagine this is an 8-foot room. We'll say this is 8 feet, just so the numbers will look nice. And maybe instead of crossing 1 foot at a time, you cross by 2 feet. It might be difficult to walk 1 foot, but we can walk 2 feet at a time. So this particular path is going to be the path that you take if you travel 2 feet at a time. So each time you're going to step 2 feet across, so 2 feet. So one step takes you 2 feet. If you take another step, that's going to take you 4 feet to the center of the room. Take another step, that's going to take you 6 feet. And then one final step, and you will end up at the other side of the room, directly against the wall. Now, what if instead of traveling 2 feet at a time, I'll write 2 for each of these, so 2 feet at a time. Again, what if instead of traveling 2 feet at a time, you walked the distance from one side to the other by just cutting the distance in half each time? So if this distance you're going to travel is 8 feet in total, then that means the first step you would have to take if you're going to cut that full distance by half each time you take a step, the first distance you would travel would be 4 feet. So you would cut that 8-foot distance in half, which means your first step, more like a jump, is going to be a 4-foot jump. So now you're starting from this particular location, and again you're trying to make it to the other side of the room to hit this wall. Well, you now have 4 feet left to travel. And again, each time you take a step, you're going to cut your distance by half. So this additional 4 feet, if you cut this in half and take another step, that means over your next step, you're going to travel 2 feet. Well, you now have 2 feet left to make it to the other side, but again, you're cutting the distance by half. So your next step, you're going to travel half of that, which is 1 foot. Keep going. We now have 1 foot left to get to the other side of the room. Travel half the distance. Well, that means you would now travel half a foot. And then and so on and so forth in the same kind of way. So the next step would be 1/4 of a foot, and then 1/8 of a foot, 1/16 of a foot, so on and so forth. Now you might be looking at this particular path and thinking, how on earth could I do this? How could I step half a foot? My foot itself is probably longer than half a foot. Well, I want you to imagine for a moment, instead of being actually a physical human being, actually taking up space, having mass, imagine you're the size of a single point, like a single point on the coordinate plane, something that's infinitely small. And imagine that point traveling that distance. So your point travels 4 feet, and then 2 feet, and then 1 foot, and then half a foot, and then 1/4 of a foot, and then so on and so forth. So one thing to think about by taking this particular path, traveling as a point, something infinitely small, along this path, one thing to think about is how long will it take for you to actually make it all the way from one wall to another? Well, what's going to happen is we're going to keep cutting the distance by half. Each time we take an additional step, we're going to cut the distance by half. But the problem here is by cutting this distance by half every time, we're getting closer and closer and closer to this wall But as it turns out, we're never actually going to make it all the way to the other wall. We keep cutting the distance by half, which means we get closer and closer and closer. And surely if, you're talking about an actual human walking across the room, eventually you're going to run right into the wall. Either your toe's going to hit it or your nose is going to hit it. But if we're talking about something the size of a single point that continues to travel across the room, well, if we just continue cutting the distance, yes, we get really, really close to the other wall, but we're never actually going to reach it. You will never actually be able to make it all the way across the room just by cutting the distance by half each time you take a step. So with this first path, you can make it all the way across 8 feet, traveling 2 feet at a time. But across this second path, you'll never actually reach the wall. But you might be thinking, okay, well, I'm going to be so close to the wall, it doesn't really matter. And the response to that is yes, you will essentially be so close to the wall that it doesn't matter. But truly, you will never get to the point where the distance between you, wherever you are, and the wall, you will never get to the point where the distance between you and the wall is 0. Along this first path, you take 4 steps, and the distance between you and the wall is now 0. Along this second path, you can continue this particular procedure over and over and over again, and you're never actually going to get to the point where the distance between you and the wall is 0. But it gets so close to 0 that for all intents and purposes, we could say eventually you do reach it. You never truly reach the wall, but you get so close to the wall that it doesn't even really matter. That is the concept behind a limit. What we could say is that the limit of the distance between you, wherever you are, and this particular wall that you're trying to reach, the limit of that distance is 0. So although you never actually get to where the distance is truly 0, the limit of your distance is 0. In other words, you get so close to a distance of 0 that it almost doesn't even matter. Now, as it turns out, this word limit can be used in a couple of different ways. Along this first path, we truly do reach a distance of 0. In other words, the distance between you and the wall is truly 0. We could also say that the limit is 0 in that case as well. So a limit can represent a value that we can actually reach, as well as a value that we just approach. That's the term we're going to use. To say that we're getting really, really close to it, but potentially never actually reaching it, we're going to use the term approach. So in this case, the distance between us and this wall approaches 0. And that's going to be the fundamental concept behind a limit. This idea that we get so close that it almost doesn't even matter. We're not going to truly reach 0 or whatever value we're talking about, but we're getting so close that it almost doesn't even matter. That is going to be the fundamental concept of a limit. So again, in procedure 2, if you were to literally do this procedure, assuming you were the size of a single point, not something that physically has mass, takes up space, if you were the size of a single point, literally crossing the room by half at a time, you will never reach the wall. You'll get infinitely close, but you'll never actually reach it. So rather than saying that you'll get to the point where the distance between you and the wall is 0, we can say that the limit of the distance between you and the wall is 0. In other words, your distance is approaching 0. We're getting so close, we're getting infinitely close. We never truly reach 0, but we get so close that it almost doesn't even matter. So that's the idea behind a limit. When we talk about limits, we're going to talk about limits from the standpoint of inputs and outputs. So one of the fundamental concepts in calculus is analysis of how function values, so imagine taking a function, we're talking about the actual values a function can take on, function values, otherwise think of these as outputs, function outputs, how these values are changing as function input values change. So if we allow our inputs, what we normally call x values, to change in a specific way, what's happening to our outputs, our function values, our y values? So suppose we have some function that we'll call f of x. So in discussing limits, this idea of what a limit is, what we're analyzing is how our y values behave what sort of behavior we see, what are they doing, how our y values behave as our x values, our inputs, get closer and closer to some number that we're going to call a. So as our x values get closer and closer and closer to a specific number, if our corresponding y values then approach some other number that we're going to call L, think of this kind of like the distance. What's happening with the distance? Is it approaching a specific number? It's approaching 0. What value are our y values approaching? What are they getting really, really close to? If they approach some number that we call L, specifically on both sides, so as our y values approach from above, from below, if they're approaching this value that we're calling L, this particular y value, then this number L is what we call the limit of our function, the limit of f of x as x approaches a, whatever a is. So again, the general idea is we're tracing our x values, we're following the x values on our function, on our graph, and we're allowing them to approach some number. So we're looking to the left, we're looking to the right, and we're allowing our x values to approach some number in the middle from the left and from the right. In analyzing a limit, we're asking the question, as our x values do this, what are the corresponding y values doing? Well, if we allow our x values to behave in this way and then analyze our y values, if our y values are also specifically approaching some number from both sides, then this number is what we call the limit of our function, the limit of these y values as our x values behave in this particular way. So let's look at this in the context of an actual function, an actual example. And we're going to look at both ways, graphically and numerically, both ways that we can analyze the limit of this particular function. So let's start with a really basic function. We're going to let f of x be 2x plus 3, so a linear function, and we already have it graphed here. So we have a y-intercept at positive 3, and then this line has a slope of 2, so our rise over run is 2 over 1. We want to find the limit of this function as x approaches 2. So first off, think about the x-axis. Imagine traveling along the x-axis towards x equals 2, which would be right here. Okay, so the general idea is we're tracing the x-axis from the left-hand side and the right-hand side of this value. And there at x equals 2, I'm going to put a dotted line just so we have a mark for it along the whole coordinate plane. Okay, so in analyzing the limit of our function as x approaches 2, what we're doing is we're looking at what happens as we approach 2 from the left and as we approach 2 from the right. And the specific question we're asking is, as our x values behave in this specific way, what are the corresponding y values doing? In other words, if we were to trace the graph corresponding to the x values, moving from left to right and from right to left, as we trace the graph corresponding to those x values, what specific y value are we approaching, if anything? So from the left-hand side, as we approach x equals 2, imagine tracing the graph corresponding to that particular set of x values going from negative infinity to 2. As we trace the graph approaching x equals 2 on our graph, what we're approaching is going to be this value right here. So as we approach x equals 2 from the left-hand side, our y values are getting closer and closer and closer to what looks like x equals 7. So as we approach x equals 2 from the left-hand side, the y values are getting bigger and bigger and bigger and bigger, and once we get to x equals 2, our y values have gotten up to 7. Now what about the other side? So as we approach x equals 2 from the positive side, from positive infinity backwards towards 2, what's happening to the y values there? Well, now we're looking at a portion of the graph that's way up here, but imagine moving from right to left, we would be tracing this graph, and as we get closer and closer and closer to x equals 2, the y values also are getting closer and closer and closer to 7, but we happen to be approaching from above. So for this particular portion of the graph, we're approaching from above, And for this particular portion of the graph, we're approaching from below. But what's important is the fact that we're meeting there in the middle at 7. If we look at the left-hand side of x equals 2 and we look at the right-hand side of x equals 2 and the corresponding y values, we can specifically say that those y values are meeting there in the middle at this same particular location at y equals 7. So 7 is going to be the limit of f of x as x approaches 2. So the way we can say this is as x approaches 2, as we see this specific behavior from our x values, as x approaches 2, and it's implied that we're approaching both from the left-hand side and from the right-hand side. As x approaches 2, we can say that f of x approaches, again from both sides, f of x approaches 7. So the limit of f of x in this case is 7. Now this limit is specific to the particular x value we're talking about approaching. If we were discussing x approaching a different value, we would have a different limit. So these two numbers are paired very specifically. The limit can change if we're talking about approaching a different x value. This happens to be the y value that we're approaching as our x values approach 2. So we can see this from the graph just based on the fact that we look from the left, we look from the right, and we see the same y value being approached as our x values approach x equals 2 from either side. Now what does this look like numerically? When we talk about evaluating a limit numerically, we're looking at actual individual x values and then the corresponding y values that we see. So again, we're looking to the left and the right. In other words, as we approach 2 from the negative side and as we approach 2 from the positive side. So when we analyze a limit numerically, what we want to do is determine what happens as we input x values to our function that grow increasingly close to 2, either from below, from the left-hand side, or from above, from the right-hand side. And typically what we'll do is we'll end up generating repetitive decimals that get closer and closer and closer to the number in question. So for instance, if we're approaching 2 from the left-hand side, from the negative side, we might ask the question, well, what's happening for an x value of 1.9, which is really close to 2? Or maybe a little bit closer, which would be maybe something like 1.99, a lot closer. So this is 1/10 away, this is 1/100th away, or what about 1.999, which is 1,000th away, even closer. The idea is we're generating these x values that are getting closer and closer and closer to 2, and we're analyzing what happens for those particular values. Now we'll look at that in the calculator in just a minute. Now the same thing from the other side. We need to analyze what's happening on both sides, approaching both from the left and from the right. But now we're approaching from values that are larger than 2. So furthest out, but still close to 2, something that's larger, maybe something like 2.1. So 1/10 away, but now 1/10 away, and it's above. Or maybe something like 2.01, which is 100th away, but again above 2. Or something like 2.001, which is again really, really close, but above 2. When we analyze the limit of our function, we're asking the question, do we see the same behavior on the left-hand side and on the right-hand side as our x values approach 2? What are the function values doing at all of these locations? And this is going to be a great time to use the graphing calculator so that we can get these individual values. Now you do have a couple of different options here. Technically, you could just plug, for instance, 1.9 into your function. You would do 2 times 1.9 and then add on 3, and that'll give you your function value. That's certainly an option. The actual graphing utility, specifically the table function in your graphing calculator, is going to be really beneficial here. It's going to be a great time saver. So let's go in and input this function, 2x plus 3, into the graphing utility. And of course, we know what the graph looks like. That was already generated. What we want more specifically is going to be the table. So it's right above graph in blue. That means you access it from second. So second and graph will take you into the table. And more than likely you'll have a table that looks like this. The specific thing to notice is how the x values are changing. So as we look at these individual x values, they're increasing and decreasing by 1 unit at a time. Now we want to analyze what's happening for values that are decimal, that have particular decimals that aren't integer values. So how do we do that? We can't actually see those on the table. Well, there's a couple options. This is going to be the easiest option. We're going to have to change our table settings. So I'm going to go into table settings right above window in blue. So second and window takes us into our table settings. So table start says this is the lowest x value that we see. And then that little triangle symbol, that's actually a delta symbol. That is change in table. That tells us how the x values are increasing from where they start and then continuing on. What we're going to change is independent. Independent represents the x value on our table. Dependent represents the associated y value. So independent being set to auto means the table is going to automatically generate all the x values and then the corresponding y values automatically, just based on these start and change settings. What we want to do is change from independent to ask. So I'm going to scroll down. Auto is highlighted now. I'm going to highlight ask and I'm going to press enter. Now let's go back into the table. So second and graph takes us back into the table, and notice it's empty. That's not a problem. The reason it's empty is because now it's set up to allow us to type in our own chosen x values and then see what happens with those specific x values in terms of corresponding y values. So first value we want to evaluate with is going to be 1.9. And so if I plug in 1.9, the table tells me that the corresponding y value is going to be 6.8. Okay. What about our next y value? Again, the idea is we generated these values that are getting closer and closer and closer to x equals 2. So our next one was 1.99. Well, that's going to take us to 6.98. So notice we increased just a little bit. What about 1.999? Okay, getting a little bit closer. Well, 6.998. So what's happening? We're increasing, starting at 6.8, increasing just a little bit at a time, but we're asking the question as these values change, are they approaching something? Are they getting closer to a particular value in this continuing fashion? And because we continue to increase, but we're increasing in this specific way a little bit at a time, what would happen if we went a little further? That would be a little bit further. Well, again, same kind of pattern. What's happening? As we get closer and closer and closer to an x value of 2, the y values are getting closer and closer to a value of 7. So from the left-hand side, we're approaching a value of 7. Now what about as we approach from the other side, from the right-hand side, from the positive numbers? Well, let's start out with the furthest out number, which was 2.1. So at x equals 2.1, we are at a y value of 7.2. Okay, let's get a little bit closer. So 2.01. That's going to take us to 7.02. So still bigger than 7, but now we're getting closer and closer in the same kind of fashion that we saw before. What about 2.001? So again, still above 2, but even closer. Well, that's going to take us even closer to 7. So 7.002. And again, in the same fashion, if we continue to generate these corresponding x values, again, we see the same kind of behavior with the y values. So from this particular direction, our y values are also approaching 7. Now what happens at 2 itself? Let's input a 2. At 2 itself, the associated y value is 7. So this in particular tells us that f of 2 is equal to 7. So the actual function value at x equals 2 is going to be 7. That's the y value associated with an x value of 2. When we're looking at a limit, however, What we're interested in is what's happening on either side of that particular x value in question. Not specifically what's happening at 2, but what's happening to the left of x equals 2, what's happening to the right of x equals 2. Because we see the same behavior on the left as we do on the right, because we approach a value of 7 from the left and we approach a value of 7 from the right, that is the indication that our limit has a value of 7. Now you might be wondering, why does that really matter? We know we hit 7 right there in the middle. Well, there will be certain functions that won't behave as nicely as a linear function where we actually meet in the middle at a true point. We'll see some slightly more exotic situations where we approach a value from a left and we approach a value from the right, but there in the middle, different kinds of things happen than what happened right here. So limits in general are not typically used for a function like this where everything behaves nicely. Typically we use limits in this type of analysis to look at situations where maybe things don't behave the way we normally like. Maybe there's some holes in the graph, some gaps in the graph. If we can analyze what's happening from the left and the right, but maybe not worry so much about what's truly happening in the middle, that's going to be the way we tend to use limits. Okay. So let's formally define our notation and what a limit formally means. So rather than having to say in words the limit of f of x as x approaches 2 is 7, we have a shorthand notation for representing this. So as x approaches a, again we're just going to use a generic x value, as x approaches this particular value, the limit of f of x is L. We want to represent that statement. As x approaches a, the limit of our function has the value L. The way we would write this is the limit, which we'll abbreviate as lim. Under lim, we're going to write the value that x is approaching. So the limit as x approaches this particular value, this specific number that we're calling a. A will be an actual number when we're looking at our problem. For the previous problem, it was 2. So the limit as x approaches a of f of x, we'll just write f of x next to that. So all of this goes together. The limit as x approaches a of our function f of x is equal to L, and that would be our value. So for the problem we just looked at, a would be 2 and L would be 7. The limit of our function as x approached 2 was 7 because 7 was the value that we were approaching in terms of our y values, both as our x values came at 2 from the left and as they came at 2 from the right. So we can use this notation. We can say that our limit is L, whatever that number L happens to represent, if all values of f of x are close to L, if all of our y values, our outputs, are close to L, when we look at values of x that are sufficiently close to a. So essentially think of that in terms of the table. If we look at values of x that are getting really, really close to this particular number, the number we're approaching, if there are also corresponding function values approaching a particular number on both sides, when we look close to this number a, if we have a particular y value that we're approaching in terms of our function values as our x values approach a, then that particular value represents the limit of our function. Also, if the limit exists, then it is unique. In other words, we can't be approaching two different things at the same time when we talk about a limit. Now, for a limit to exist, for this particular expression to be defined, to say that this limit is equal to L, it's important that we approach this number a from both sides. We have to look at what's happening on both sides of our number. So again, for instance, with the previous one, we looked at x equals 2. We looked at it from both sides. It was important that we saw the same behavior on both the left-hand side, approaching 2 from one side, and then on the right-hand side, approaching 2 from the other side. It was very important that we approached the same y value on both sides. That being said, we can also define something called a one-sided limit. If all we care about is looking on one side versus the other side of our particular x value, then we'll use what we call a one-sided limit. So a left-hand limit allows us just to look at what's happening on the left-hand side of a number as we approach from the negative direction. And we're going to use essentially the same notation with one particular addition. So we're going to use the same limit notation. X is approaching our number, but in order to indicate that we're approaching from the negative side, from the left, we're going to put a little superscript negative symbol next to the number that we're approaching. So this is the limit as x approaches a from the negative side, in other words from the left-hand side of the coordinate plane, of our function f of x. Now the same thing if we're approaching from the right-hand side, but now we're approaching from the positive side of the coordinate plane. So our notation there would be limit as x approaches a, but now we're approaching from the positive side. So we're going to use a little positive superscript there. And again, we're taking the limit for our function f of x. For the general limit to exist, both of these, the left-hand limit and the right-hand limit, must be the same. So we actually looked at these two limits without knowing it in the previous example. So when we looked at what was happening on the left-hand side of 2, this was analysis of a left-hand limit. From the left-hand side of x equals 2, in other words, looking at x values that are smaller than 2, we demonstrated that the associated y values were approaching 7. So we would say that for this function, the left-handed limit as x approaches 2 has a value of 7. The right-handed limit also had the same value. As we looked at x values that got closer and closer to 2 but were larger than 2, we also demonstrated that the associated y values approached 7. So because we were approaching the same value in both directions based on the left-hand limit and the right-hand limit, that was our indication that we had that existing limit there in the middle. We'll find that if we approach a different value from each side, which is possible, it's not possible for a function like this, but it will be possible for other types of functions. If we approach a different value from the left and from the right, all we can say at that point is that the general limit does not exist. The individual left-hand and right-hand limit exist, but the general limit approaching from both sides does not exist. The only way that general limit will exist is if the individual limits from the left and right are the same. Now, based on the previous example, why couldn't we just plug into the original function and find f of a and use that to evaluate the limit? Why do I mention that? Well, notice we can sub in f of 2. So if we subbed in x equals 2, since we were analyzing what happened around 2, around x equals 2, if we were to just sub in x equals 2 at the very beginning, f of 2 would be 2 times 2, which is 4, plus 3, which would give us a value of 7. And we said our limit was 7. The numbers were the same. So why did we have to graph it and look at it from the graph? Why did we have to look at it from the standpoint of a table if the actual value we were looking for was just the y value we would have gotten plugging in 2 at the very beginning? Why did we have to go through all of that in order to make that determination? Well, the reason we had to go through all of that when the function value was the same thing as the limit value is because those two numbers are not always going to be the same. So let's look at an example where maybe it's not as clear-cut, maybe the same kind of thing doesn't really happen. So here's our new function. We have a rational function. We're going to call this g of x. So g of x is defined as x squared minus 1 quantity over x minus 1. So first thing is we want to find g of 1, evaluate it, and then we also want to find the limit of g of x as x approaches 1. In other words, the limit of the function, what are the outputs doing as the x values get closer and closer to a value of 1. But we're going to start with the actual function value. Let's see what happens there. So g of 1 is just saying take the rule for g and sub in a value of 1 in place of all of our instances of x. So that would be 1 squared minus 1 divided by 1 minus 1. And so in our numerator, 1 squared is 1, 1 minus 1 is 0. And then our denominator, 1 minus 1 is also 0, which is undefined. So this is a little bit different than the previous example. In the previous example, the function value at the particular x value we were interested in happened to coincide with our limit. Okay, here the function value at the x value we're interested in doesn't actually exist. It's actually undefined. So that means just subbing it in and maybe taking that kind of shortcut, that's not necessarily going to work in this case. So we're going to have to look at the graph, we're going to have to look at the numbers and analyze it from that standpoint. So let's start by graphing it, and we'll graph it in here and then we'll talk about what we can see from the actual function itself. Now, whenever you type in a rational function to graph, you want to make sure you have parentheses around the entire numerator as well as parentheses around the entire denominator. Leaving those off absolutely makes a difference. So parentheses around the numerator, parentheses around the denominator, and then let's graph it. Let's get a picture. Okay, why does this look the way it does? It looks like a line. Well, it looks like a line because something very specific is happening with this particular function. With this function, if we were to factor the numerator, we would have something that cancels in the denominator. Normally when we look at a rational function, we see much more exotic graphs. Here, this is a little bit different because of how the numerator and denominator are related. Now, just for the moment, let's go back into the table settings and let's just set the table up to be where it was before. So let's go back and let's put the independent variable on auto, which means the table will just generate itself automatically. And then I'm going to graph it again. It still looks the same, but I'm going to go into the table. Okay. So let's just graph using the ordered pairs and let's see what we can see. So I have x equals -4. So at x equals -4, our associated y value is -3. So there's going to be a point there. Okay, at -3, we're at -2. And then -2, we're at -1. Okay, at -1, we're at 0, so there's an x-intercept. At 0, we're at 1. And then when x equals 1, there's an error. That means there's somehow a gap in the graph. And that can mean one of two things. It means something very specific here. So let's skip over that, and then let's go on to the other side. So when x is 2, 1, 2, 3. Okay. When x is 3, we're at 1, 2, 3, 4. When x is 4, we're at 1, 2, 3, 4, 5. By this point, it should be pretty clear what exactly is happening in terms of the shape of this graph. It's not going to suddenly do something really strange. It's pretty clear that these points are going in a line, and we saw that from the graph as well. So the graph of this function, even though it's a rational function, and normally we don't see this, the graph of this function is a line. But that's not quite the whole story, because remember, there's that error there in the middle. There at x equals 1, there is no y value, which means there's actually a hole in the graph right there at x equals 1. So the graph of this function is linear, except that we have this one gap right there in the middle at x equals 1. And again, I'm going to put a dotted line in here so we know exactly where we're looking at. This is the particular location we're interested in. Okay. So now what we're interested in is the limit of our function as x approaches 1, as it approaches this location. So just like before, we're asking the question, what's happening on the left-hand side as we come at x equals 1 from the left, and what's happening on the right-hand side as we come at x equals 1 from the right. Well, as we approach from the left, our y values are getting bigger and bigger and bigger and bigger. And it looks like they're getting closer and closer to this particular location. Now remember, there's a hole right here, but in terms of what we're approaching, what we're getting close to, as we continue towards x equals 1, we're approaching that hole, and that hole is at a location of y equals 2. That's where the hole is located in terms of its y coordinate. It's there at y equals 2. Now, as we approach x equals 1 from the right-hand side, we're approaching from above, the y values are bigger. But again, as we get closer and closer and closer to x equals 1, the y values are approaching the location for our whole, which again is at y equals 2. So we can say as x approaches 1, because again that's the x value we're interested in, as x approaches 1, f of x, or in this case g of x approaches from both sides the same value. From the left, the y values are getting closer and closer to 2. From the right, the y values are also getting closer and closer to 2. So another way of saying that using our new notation is the limit as x approaches 1 from both sides, since we demonstrated the same thing happens on the left and the right, the limit as x approaches 1 of this function, g of x, is the value 2. But how is this different from the previous example? It almost looks the same. Well, it's different here because this actual value we're approaching, there's not really anything there on the graph. There at x equals 1, where we're interested in, there really isn't anything there. There's a hole there. So we're getting closer and closer and closer to y equals 2, but there isn't actually a point there at 1, 2. There's a hole in the graph. So we can't say that there's a function value associated with 1. We would say that 1 is outside of this function's domain. If we plug it in, we end up with something that's undefined. But we can say that the limit of the function is 2, because if we look at the left-hand side of the hole, if we look at the right-hand side of the hole, we're getting closer and closer and closer to the same number on both sides. So that's what we'd see from our graph. Now what about looking at this numerically? So same idea, but now we're looking at the table. We're approaching 1 from both sides. I'm going to go back in and I'm going to adjust my table setting again. I'm going to change my independent variable to ask so we can type in whatever numbers we want. And then I'm going to go back into the table and again it clears out. So what x values do we want to look at? Well, we want to look at x values that are smaller than 1 but getting close to 1. And then also x values that are bigger than 1 but getting close to 1. So smaller than 1, if we were to go maybe 1/10 less than 1, which is still pretty close, that would be 0.9. 1/100th would be 0.99. 1,000th would be 0.999. You'll start to get a sense of what these patterns are going to look like. And then maybe 1/10 above, which would be the furthest out number, that would be 1.1. If we were 100th above, that would be 1.01. If we were 1,000th above, that would be 1.001. So again, bigger than 1, but increasingly close to that x value of 1. Now here at 1, remember it's undefined. We demonstrated that. You can actually see that from the table as well. So what happens if we type in 1 and evaluate it? It's going to give you the error. The error means again that there's nothing there. And here, that error, the fact that there's nothing there, means there's a hole. There's not an asymptote that we sometimes see with rational functions. There's just a hole in the graph. But now we want to see what happens with those x values that approach 1, either from the left or from the right. So for 0.9, our associated y value is 1.9. Okay. For 0.99, a little bit bigger, we get an output of 1.99. You can probably guess what's going to happen with the next one just based on the pattern. 1.999. So again, we increase by small amounts, but we're clearly getting closer and closer and closer to a particular value, and specifically this value is 2. Now we also need to analyze what's happening on the other side. So here we would say that the left-handed limit, if we want to write a notation for this, we could say the limit as x approaches 1, but specifically from the left-hand side, so from the negative side. The limit as we approach from the negative side for this function g of x is 2. So the left-handed limit for this function as we approach x equals 1, the left-handed limit takes on a value of 2. Now we want to look at the right-hand side as well. So let's start further out. So 1.1, we plug that in, we get an output of 2.1. A little bit closer, 1.01, we get an output of 2.01. And again, you can probably guess what's going to happen with the next one. These patterns do seem to be pretty consistent. So we're at 2.001. So again, we see the same kind of behavior. As our x values get closer and closer to 1, they're in the middle, our y values, our function values, are also getting closer and closer and closer to 2. So this particular behavior, if we were to write that in notation, we could say that the limit as x approaches 1 from the positive side, from the right-hand side, the limit of our function is also 2. What we're interested in now is the fact that these two limits are the same. So the left-hand limit has a value of 2. The right-hand limit also has a value of 2. Because those two limits are the same, we can say that our general limit as x approaches 1 has a value of 2. But again, the thing to notice here is that we don't truly meet in the middle the way we did with the previous example, where there was actually a point associated with the x value that we were analyzing around. Here at that x value, there's really nothing there. So analyzing using the limits is really the only thing we can do, since we can't actually evaluate and find a specific value at that location. Okay. Another situation similar to this one, where we can't truly evaluate the function at a particular location, but we can analyze what's happening on either side at that location. Similar to this is the situation where we're looking at a piecewise function. So piecewise functions, those are functions that are defined in pieces. So like a piece of pie, a piece of pizza. Piecewise functions. A piecewise function has more than one function rule. Different rules apply to different portions of the domain, in other words, different x values. So for some x values that you would plug in, you would follow one rule. For other x values, you would follow a different rule. So here our function h of x is a piecewise function. And then if x is less than 1, so for any x value less than 1, this would be the rule you would use to evaluate the function. For any x value that's greater than or equal to 1, you would use this rule instead. Notice what we're splitting here around, though, is x equals 1. So something's happening there at x equals 1. That's where we split and move from rule 1 to rule 2. So when we graph this, we're using the graphs of both of these functions, but we're only going to keep the portion of the graph associated with the x values that pertain to that particular rule. And again, the break is going to be at x equals 1. So just like before, I'm going to put a dotted line there at the x value in question where we're splitting off. So there at x equals 1, that's where we're splitting off. Okay, so in order to graph this particular function, we're going to have to graph one rule at a time. So let's start with the first rule. This corresponds to all the x values that are less than 1. So in other words, the left-hand side of the graph. It's going to be linear. We have a y-intercept at positive 2, which is going to be right there. And then our slope is 2, which we can think of as 2 over 1. So rise over run, rise 2, run 1. Okay? And so that is going to be enough to graph that one. It's going to be linear, but I'm not going to connect the dots all the way across the coordinate plane because, again, keep in mind this function rule only applies for x values that are less than 1. So we only want the portion of the graph corresponding to the left-hand side of the x-axis. So it's going to look something like this. And again, we don't trace the right-hand side. Now we're going to have to be careful here. Notice this only applies when x is strictly less than 1. So this particular point here at 1, there's actually going to be a hole there. There's not truly going to be a point there, because to include the point there, we then have to jump to the next rule. So there at x equals 1, we're not following this rule anymore. we're following the next rule. So we get really, really close to that particular location, but we don't include that point because it's not included as corresponding to that first rule. So there's truly going to be a hole right there when we reach the boundary and jump from rule 1 to rule 2. Now for this next one, we have a y-intercept at -4 and then a slope of 2. Now -4 technically is over here, which is on the wrong side, but I'm going to mark it just really lightly, just so we have somewhere to start. So that's going to be our y-intercept for this next portion of the graph. And again, we have a slope of 2. So rise 2 and run 1. And here, this particular rule does correspond when x is equal to 1. So this particular location, this particular point, will truly be colored in because this will be a point that we include. So again, I'm going to connect my dots, but I'm not going to trace the whole thing. This particular rule only applies when our x values are greater than or equal to 1. In other words, the right-hand side of the coordinate plane. So I'm just going to connect the dots on the right-hand side. And so those two graphs put together, included, those represent our actual function. So one piece corresponds to rule 1, one piece corresponds to rule 2. That's going to be our graph. So let's look at some limits based on this graph, both, again, numerically and graphically. So first thing we want to look at is the limit as x approaches 1. Okay, so again, that boundary. We're interested in what's happening on the boundary. So there at x equals 1, we have to look on the left, we have to look on the right. So approaching from the left and then approaching from the right. Now as we approach from the left, approach x equals 1 from the left, as we trace our y values and get closer and closer and closer to this x value in question, our y values are getting closer and closer and closer to the value y equals 4. So the way we could say that is that the limit as x approaches 1, as our x values get close to 1, the limit as we approach 1 from the negative side of our function, well, the y values are getting closer and closer and closer to y equals 4. So the limit is equal to 4. Now what about the other side? What about the limit as we approach 1 from the positive side for our function? Well, as we approach 1 from the positive side, trace that portion of the graph, the y values are getting closer and closer and closer to, looks like, -2. So there we're at y is equal to -2. So as we trace our function and approach x from the positive side, the y values are approaching -2, which means the limit from the right-hand side is going to be -2. Now from the left, we approach 4. From the right, we approach -2. Notice we're approaching two different points if we look on one side or the other. These are not meeting in the middle, so as we approach from the left, approach from the right, we're not meeting in the middle at a common location. So because the left-hand limit and the right-hand limit are equal to different values, we're approaching different function values, different outputs, that is actually our indication that this limit, this general limit, does not exist. Since we're talking about approaching 1 in general, we're saying both sides. What are we seeing on one side versus the other? We need to see the same behavior on both sides to say that this general limit exists. Because we see something different on the left than we see on the right, that's our indication that the limit does not exist. Okay, now how would we do this numerically? This is going to be slightly more complicated just because we have two function rules and we're going to have to be careful there. So let's start with the first rule. Let's just graph that. So I'm going to go back in here. I'll clear out our previous function. We're going to graph 2x plus 2. Okay, go into the graph. Now remember, that's not the whole story. We're only keeping a portion of that graph. So the only portion of that graph we really want to pay attention to is the portion corresponding to x values that are less than 1. So anything corresponding to an x value greater than or equal to 1, we're going to ignore that. Okay, so that is going to be the rule we follow as long as we're less than x, as long as we're on the negative side of this x value at 1. So what sort of x values could we use to analyze what's happening on the left-hand side of 1? Well, again, maybe something like 0.9, 0.99, 0.999, things that are getting closer and closer and closer to 1, maybe not quite reaching there. So what's going to happen in the table? Okay, let's see. So we can just use those. So 0.9, notice we're at 3.8. Okay, looks like we've already got the values we want. 0.99, we're at 3.98. 0.999, 3.998. So clearly we're approaching a specific value, which would be 4, which again corresponds to our left-hand limit of 4. Okay, now at 1, we're saying the y value is 4, but that doesn't actually correspond to our function. Remember, when x is equal to 1, we've now jumped and we're using the other function. So this point at x equals 1 and y equals 4, that's where we had the hole in the graph and where we jumped from one piece of the graph to the next. So when we analyze the other side of 1, what happens for y values that are, x values that are bigger than 1, now we're going to have to use the other function, the other rule. So the other rule was 2x minus 4. That's going to be the rule that corresponds to everything on the other side of 1. So again, that's the graph we're looking at now, but we're only going to look at the portion of that graph corresponding to x values that are 1 or larger. So let's look at the table there. Now we're looking at 1, things that are bigger than 1. So approaching 1, this would be 1/10 away, 100th away, and then 1,000th away. Okay, so what happens for those values? Again, we already have those in the table. So when we're at 1.1, our y value is negative 1.8. 1.01, the y value is negative 1.98. And then just a little bit closer, negative 1.998. And again, we're seeing similar behavior, but very different numbers. But it looks clearly like we're approaching a particular y value. In this case, the value we're approaching is going to be negative 2. Now here at 1, what happens at 1? Well, remember, when x is equal to 1, we're following the second rule. So when x is equal to 1, we're going to use the value from this particular table, which would be negative 2. So at this particular point, this corresponds to h of 1 being equal to negative 2. Okay, but again, if we're interested in the limit, we're trying to determine what is the limit of our function as x approaches 1. Well, as we approach from the left, the values indicate that our function is approaching a value of 4. And as we approach 1 from the right, the values are approaching a function value of negative 2. Because those don't meet in the middle, because there's that gap, we're not meeting, we're not approaching the same value, that again is confirmation that this limit does not exist. Now that's at the boundary. That's the boundary where we broke between rules. Let's look at a different limit approaching a different x value. So what happens as we approach x equals negative 3? Well, first off, which one of the rules is that going to correspond to negative 3? Well, negative 3 is going to be less than 1. That means this particular rule is going to correspond to an x value of negative 3. So I'm going to make a note of that. There for negative 3, that would only be rule 2. And that's not a boundary value or anything, so if we look right to the left of negative 3, right to the right of negative 3, we're still looking at x values that are evaluated using that second rule. Now what happens specifically at negative 3 itself? Well, we can actually just plug it in and probably do it mentally. So x is less than 1, negative 3 is less than 1, which means we're using rule 2, or rule 1, excuse me, to evaluate it. So 2 times negative 3 would be negative 6, and negative 6 plus 2 would be negative 4. So there at negative 3, the associated y value would be negative 4. Okay, so again, this corresponds to h of negative 3 is equal to negative 4. Okay, what about the limit though? What's happening on either side as we approach negative 3 from the left, as we approach negative 3 from the right, what's happening? Okay. Well, if we're approaching from the left-hand side, that's numbers that are more negative. So going towards negative 4, towards negative 5, so on and so forth. So a little bit more negative would be something like negative 3.1. A little bit closer would be something like negative 3.01. And then just a tad closer would be 0.001. Now on the positive side, we want numbers that are again close to negative 3 but larger, more positive than negative 3. So pretty close would be negative 2.9. A little bit closer, negative 2.99. Again, we're going now towards negative 3. And then something like negative 2.999. Okay, so ignore what's already in the table. We're just going to type in everything else we need. Okay, so now we want to analyze what's happening to the left. Now, what's the problem here though? Remember, we need to double check the rule. Let's make sure we're using the correct rule. So here we're talking about x equals negative 3, which means we want to use the first rule. So we're going to delete what we already have in the calculator and make sure we put in the correct rule to follow. So 2x plus 2 is the rule that we're going to follow. And let's go back into the table. Okay, so let's start with negative 3.1. So negative 3.1. We evaluate there. That's going to give us a value of negative 4.2. Notice it just wrote over what we already had. That's fine, or you can start below the list as well. So at negative 3.1, our associated output is negative 4.2. A little bit closer to negative 3, negative 3.01. We're at negative 4.02. And again, you'll probably start to see the patterns with these. Negative 3.001. And we're at negative 4.002. So we're getting closer and closer and closer to a value of negative 4, okay? Which makes sense based on the function value we have as well. From the left-hand side, we're approaching negative 4, and at negative 3, we're at negative 4. Now what's happening to the right-hand side? What's happening on that side? So furthest out number, negative 2.9, we have a y value of negative 3.8. Okay, a little bit closer, negative 2.99. We have a y value of negative 3.98. And then negative 2.999. And we have a value of negative 3.998. Again, similar kind of behavior. Now our numbers are getting more and more negative, but again, the idea is that we're approaching this value of negative 4. So if we look at our left-hand limit and our right-hand limit, what we can say here, using our notation, is that the limit as x approaches negative 3, that's the x value we're approaching, the limit as x approaches negative 3 from the negative side for this function, h of x, that limit has a value of negative 4. So we're approaching negative 4, the function values are approaching negative 4 as our input values approach negative 3 from the left-hand side. What about the other side? So the limit as x approaches negative 3 from the positive side for this function h of x. Well, as we approach negative 3 from the positive side, the associated function values are also approaching negative 4. So the right-handed limit has a value of negative 4. Because these values are the same, because those two numbers coincide, that common number is going to be the value for the actual limit. So our actual limit, the general limit, has a value of negative 4. So notice in this case, for this one function, one limit we evaluated didn't exist because different things were happening on each side at that particular x value, whereas this next one did exist because we saw the same behavior on either side. That can happen with specific functions where there tend to be holes or breaks. So functions that are continuous, which means they just continue left to right, we'll define that a little bit more definitively later. But functions that don't really have any holes or breaks, anything like that, typically evaluating the limit is not particularly challenging. We don't really see anything special happening. But functions like this that have a very clear break from one piece of the graph to the next, these are going to be the kind of functions where we actually do want to analyze the limit, what's happening on the left of a value, what's happening on the right of a value. And we run into issues like this, where we can't evaluate a limit in general just because different things are happening on each side. So that's going to be one situation where limits are going to be helpful there with those piecewise functions. Now, limits are also going to help us understand the role of infinity with respect to some functions. Specifically, think things like rational functions. Rational functions have these key features that we call asymptotes. Asymptotes represent locations where either our x values are approaching infinity or our y values are approaching infinity. So we can talk about infinity in a couple different ways. We can talk about situations where x is approaching infinity, or we can also talk about situations where maybe our x values are approaching a number, but then the function values, the associated y values, end up approaching infinity. So we want to look at these situations because these are going to be situations where limits become very helpful, and understanding what a limit means is going to be very helpful. So our next function, f of x, is a rational function, 1 over x minus 2. First thing we want to do is graph it, and then we want to find some limits based on that, based on the graph, and then numerically, of course, as well. So let's go back into the table settings, put it back on auto for the time being. We'll change it back if we need to. And now let's type in our function. So 1 over x minus 2, so our numerator is 1, divided by, and then make sure you put your denominator in parentheses. Just a heads up, if you leave the parentheses off, then what the calculator thinks you mean is 1 divided by x, and then take that whole thing and subtract 2 from it. It won't be including the 2 in the denominator naturally. So having those parentheses is going to be important. So let's graph that. There we go. So more what we expect to see when we look at a rational function. So we can analyze some of the things we're seeing from the table. Let's go look at the table. So the big thing that sticks out is that error. There's an error at x equals 2. Well, what's going on with the graph there at x equals 2? Well, that looks like where we have the divide. X equals 2 is where we have the vertical asymptote in this case. Notice that a value of 2 substituted in would make the denominator 0. And if you remember, that's our corresponding situation where we have a vertical asymptote. So any x value that would make the denominator 0, hence making the whole function undefined, represents a location for a vertical asymptote. So there at x equals 2, that's where we have the vertical asymptote that's breaking our graph up into pieces. Now the rule for horizontal asymptotes has to do with comparing the numerator and denominator. So anytime the degree in the numerator is lower than the degree in the denominator, we have a horizontal asymptote along the x-axis. So in this case, the numerator's degree, its highest exponent, is actually 0. We're looking for x and the exponent on x. Well, if there's no x there, it has an understood exponent of 0. And then our denominator, the highest x, has a power of 1. So numerator's degree, lower than denominator's degree, means we have a horizontal asymptote at the x-axis. And I'm putting these in as dotted lines because remember, they're not really there. These are these imaginary boundaries that break our graph into pieces. Now that's not going to be enough to get the whole picture. We've got a sense of where things are, but let's use the table to get some actual points to graph. Just graph what seems convenient. So when x is 1, we are at -1. Okay, so that point's going to be there. When x is at, let's see, 3, we're at 1. And then based on what we saw from the graph, we know that we have 2 branches, again, crossing through those particular points. One is in this particular section and one is in this section. Vertical asymptotes cannot be crossed, and in this case, our horizontal asymptote will not be crossed either. So we expect to see something like this, which is, again, confirmed by the graph we just saw. So that's roughly speaking what our function is going to look like. Okay. So let's look at what's happening numerically. So what are we looking at in terms of the limit? We want to analyze the limit as x approaches 2 from the negative side, the positive side, and in general. What's significant about x equals 2? Well, remember that's where we have that vertical asymptote. So we want to use limits to analyze what's happening on either side of that vertical asymptote there at x equals 2. Okay, so let's look at the numbers. In general, we know that there's some specific things happening there just based on the graph, but let's look at the actual numbers there around 2. So again, the left-hand side, numbers that are smaller than 2, and then the right-hand side, numbers that are approaching that are larger than 2. So smaller than 2 might be something like 1.9, 1.99, 1.999, okay, and then bigger than 2, furthest out might be something like 2.1, and then a little bit closer, 2.01, a little bit closer, 2.001. So what's happening with those specific values on the left, what's happening on the right? Okay, so let's go back and change the table to ask independent, so we can type in the values that we want. Okay, so from the left-hand side, 1.9, furthest out but close, we're at y is equal to negative 10. Okay, 1.99, well now we're at negative 100. 1.999, negative 1,000. And you can probably see the pattern. What if we went one step further, 1 point and then 4 nines? Well, negative 10,000. What's happening? They're getting larger and larger, but they're negative numbers, so they're getting more and more negative. So on this side, we're approaching, looks like negative infinity. As our x value gets closer and closer and closer to 2, the y values are getting bigger and bigger, but bigger and bigger in the negative direction. So we're approaching negative infinity. Now what happens at 2? Well, it's undefined. Remember, there's a break there in the graph. If you tried to plug in 2 to the function, you end up with 1 over 0, which is undefined. So there's nothing there at x equals 2. Now what about the other side? So what if we look at 2.1? Let's see, so the associated output is 10. 2.01, the associated output is 100. And then 2.001, the associated output is 1,000. So notice mirroring values, and you'll see the same thing if we keep going. So the numbers are getting bigger and bigger and bigger, but now they are positive numbers, so we're approaching positive infinity. So once we have these, once we know what's happening for our x values that are smaller than 2 and x values that are larger than 2, that gives us our one-sided limits. So as x approaches 2 from the negative side, from the left-hand side, our values are going towards negative infinity. So we would say that our limit is actually equal to negative infinity. Now keep in mind, negative infinity is not actually a number. Infinity is just that, it's infinite. But the idea with a limit is this is the value we're approaching. We're going off and just blowing down towards negative infinity. Does this make sense with what we see on the graph? Well, if we look at x equals 2, that's where we have that boundary. As we come at that boundary from the left-hand side, the associated y values are dropping down and getting really, really, really big, but in the negative direction. So we're going down towards negative infinity as we get closer and closer and closer to x equals 2 from the left. Now what about as approaching from the right? Well, now the outputs are getting larger and larger continually, and they're not bounded. So it's going to be approaching positive infinity. And again, that makes sense with what we're seeing on the graph. So from the right-hand side, as we approach x equals 2, the y values are getting really big. As we get closer and closer, the y values get larger and larger, again, unbounded, going up towards positive infinity. So the right-handed limit has a value of positive infinity. So from the left, we approach negative infinity. From the right, we approach positive infinity. Because we're not approaching the same value, we would say that the general limit, looking from the left and the right at the same time, does not exist. Because we're approaching different values, our general limit does not exist. So these are examples of infinite behavior in terms of the outputs, the y values, specifically as x approaches a fixed number, a constant number. Now we can also look at infinity the other way, maybe not in terms of what's happening with the y values, but what happens if our x approaches infinity. So we can also find limits with x approaching positive or negative infinity, either way. So let's use the same function, but now we want to find the values of the limits as our x values go to infinity or to negative infinity. Now how we generate the x values to check this, it's going to look a little bit different, because keep in mind we're not approaching a single fixed number, we're approaching infinity. Essentially what that means is just we're getting bigger and bigger and bigger, and the x values are not bounded, they're just getting larger consistently. So we want to sort of mimic what that looks like, getting increasingly large in terms of scale. So think of maybe a large number in terms of your x. So I don't know, maybe 1,000, something like that. Typically we use powers of 10 just to keep things nice and easy and clean. Well, something even bigger, another power of 10 might be 10,000. So that's getting quite a bit bigger. Or maybe 100,000. And of course we could go on from there, but the idea is the x values are getting really, really big. They're going towards infinity. Now keep in mind something like this is automatically a one-sided limit. If you think about what infinity means, if we're talking about x approaching infinity, that has to be approached from the left-hand side. We can't actually approach infinity from the right-hand side. So if we're talking about x approaching infinity, it has to be approached from the left-hand side. So automatically this is not a meet in the middle kind of limit, because you can't meet in the middle at positive infinity. You can only approach it from the left-hand side. So we only have to look at values that are smaller than infinity, but again, increasingly large. So we've still got the same function in. Now we want to plug in these x values and see what happens. So what happens if we evaluate for x equals 1,000? Let's see, 0.001. Okay, what about 10,000? Okay, this E, what does that mean? That is actually scientific notation. That tells you how many zeros you have in front of the decimal. So it's 1, and then take the decimal there that's right behind the 1 and move it 4 places to the left, which would give you 3 zeros. I'll show you how this looks. Imagine the decimal right there, originally behind the 1. That -4 means move that decimal 4 places, 1, 2, 3, 4, to the left, which would then give you 3 zeros. The reason your graphing calculator uses that notation is because those blanks there are hard to type in as your numbers get really large or really small. So that's going to be an abbreviated notation to indicate that kind of behavior. What about 100,000? Okay, scientific notation, 10 to the -5th. So 0.1234 and then 1. What's happening with these particular values? What are we getting closer and closer to as our x values get bigger and bigger? Well, they're still positive numbers, but the positive numbers are getting smaller and smaller and smaller, and we are approaching what looks like 0. Just really small numbers getting closer and closer and closer to 0. So the limit as x approaches infinity for our function is going to be 0. Now how can we see this on the graph? Let's flip back over. So the limit as x approaches infinity. Essentially what we're doing is we're looking at the graph and we're tracing the x-axis going out towards positive infinity. And we're asking the question, again, what sort of behavior are we seeing with the y values? What are they doing as we go further and further and out closer to positive infinity? Well, if we were to trace the graph going towards positive infinity, the y values are approaching our horizontal asymptote, which happens to be at y equals 0. So as we go towards positive infinity, our graph, our function values continue to approach y equals 0 aka the x-axis. So it does make sense based on what we're seeing with the graph. Now what happens as our function approaches negative infinity? Again, this is a one-sided limit by default. So if we talk about x values approaching negative infinity, well, the only way you can approach those is going to be from the right-hand side. So all we have to look at is numbers that are getting more and more negative, not both sides of negative infinity, whatever that would mean. So maybe something like negative 1,000, that's a pretty big negative number, negative 10,000, negative 100,000, something like that. And more than likely, we're going to see very similar behavior in terms of how the numbers look to what we just saw above. So what happens if we evaluate at negative 1,000? Okay, so negative 1, e to the negative 3. Okay, so again, same kind of idea. It's going to be a negative number in this case, and then it'll be 2 zeros because we would move the decimal 1, 2, 3 places to the left. Negative 10,000, same kind of thing, so negative number, but now we have one additional 0. Negative 100,000, again, exactly what you would expect to happen, just based on this pattern that's being established. So now we have negative outputs, but again, they're getting closer and closer and closer to a specific number. It's maybe a little difficult to see, but keep in mind that this number is actually more positive than this number. This is a bigger negative number than this particular number. So the numbers are actually getting more and more positive. They're getting smaller, but smaller in the sense that they're not big negative numbers anymore. They're getting closer and closer and closer from the negative side to that value at 0. So the limit as x approaches negative infinity for our function is also 0 because our function values are getting closer and closer to 0. And again, that makes sense based on the graph. So as we approach negative infinity, trace our graph as we go in that direction. We're getting closer and closer and closer to our horizontal asymptote, but notice we're approaching it from below. So the y values are smaller than 0, they're more negative than 0, which explains why we see negative outputs there. So let's do one final example, just put some things together. So something similar to the function we just had. Our next function is 1 over x minus 2, quantity, plus 3. And again, we want a graph, and then we're going to find some limits if they exist numerically, and then we'll verify it based on our graph. So let's input that function, see what we get. So 1 over x plus 2, let's clear that out. We want parentheses around all of that because we're going to add 3 to all of that. So 1 divided by, and here we're going to have nested parentheses. So that one set of parentheses inside for the denominator, and then close your parentheses to indicate that this whole term, we're then adding 3 to that. Okay, let's graph it. Let's see what that looks like. So it actually looks pretty similar in shape to the previous one, but we're no longer centered there along the x-axis. We've now shifted upward a little bit. As it turns out, that plus 3 is actually going to take the graph we previously saw, and it's going to just shift everything up by 3 units, including that asymptote. So what can we say about the vertical asymptote? Do we have one? Well, let's look in the table. Okay, so we need to change it back to our auto for independent. So change that back, and now let's go back to the table. Okay, there's that error at 2. So there at x equals 2, we have that error. Okay, so that means that's where our vertical asymptote is. Okay, let's plot some points from there. So when x is 1, we're at 2. So x is 1, we have a value of 2. On the other side of the asymptote, when x is 3, we have a value of 4. And then again, based on just adding 3 to the previous function expression, that just shifts everything up 3 units. So if we had a horizontal asymptote at y equals 0, if we shift that up 3 units, we now have a horizontal asymptote at y equals 3. So that will be our new asymptote. And let's make sure that looks consistent with the graph. Again, similar shape to what we saw before, but now we're just shifted to a different region of the coordinate plane. There we go. Okay, so now let's look at a few limits based on this particular function and the things we're seeing from its graph. So first off, the limit as x approaches 3 for our function. What is the limit as x approaches 3? Okay, well, remember we have to look at it from the left-hand side, from the right-hand side. So numbers that are smaller than 3, numbers that are larger than 3. So smaller than 3 but approaching 3. Getting closer and closer and closer incrementally. And then larger than 3, but again approaching 3. So getting closer to it, decreasing incrementally. Okay, so the table now has the fixed values. Let's go back and change it to ask so we can type in the values we want. Okay, so approaching 3 from both sides, so 2.9, let's see what happens there. Okay, our y value is 4.1111. Okay, a little bit closer. X is 2.99, so 4.0101. 2.999. Okay, 4.001. So what's the pattern? You can think of the ones as being sort of shifted off. So we started with a 1 in the tenths place, then we went to a 0 and a 1, then 0, 0, 1. So what's happening? The numbers are getting smaller and smaller, but they're approaching a value of 4. So from that, we could say that the limit as x approaches 3 from the negative side for this function g of x, the limit has a value of 4, since that's the value our y values are approaching. Now what happens on the other side? So how about 3.1? Okay, 3.9091. Okay, a little bit closer, 3.01, 3.9901. 3.001, 3.999. So similar kind of behavior. Think of just adding on the 9, something like that. So 9 in the tenths place, 9 in the tenths and hundredths, and then tenths, hundredths, thousandths. What's happening? It's getting larger. The numbers are getting bigger. But again, incrementally, they're getting closer and closer and closer to 4. Now we're approaching x equals 3. What happens at x equals 3? Well, let's see what the table says. At x equals 3, we have a function value of 4. So there at that middle point, we can say that f, or this is g of 3, is equal to 4. So we have a point at 3, 4, and from the left-hand side, our function values approach 4. From the right-hand side, our function values approach 4. So just to be consistent, the limit as x approaches 3 from the positive side for our function g of x is also 4. So the left-handed limit has a value of 4, the right-handed limit has a value of 4. So because these two are the same, the general limit also has a value of 4. Okay, what about approaching 2? That's a little bit different. What happens as we approach 2? Well, again, we want to look from the left, we want to look from the right. So from the left-hand side, numbers that are smaller than 2, maybe 1.9, 1.99, 1.999, getting closer. From the right-hand side, a little bit bigger but a little closer, a little bit closer still, and there we go, we analyze with those values. So let's start with 1.9. So from 1.9 we're at negative 7, 1.99, negative 97, 1.999, negative 997. Let's just see what happens if we keep going. What if we add in an additional 9? 1.9999. Well, there we go, almost negative 10,000. So in that case, the numbers are decreasing without bound. They're becoming more and more negative. So from this side, we're approaching negative infinity. Does this make sense with what we see on the graph? Let's see. So as we approach 2, what was significant about 2? Well, that was where we had our vertical asymptote. So as we approach 2 from the left-hand side, the y values are dropping down towards negative infinity. So it makes sense that we see those kinds of numbers. Now at 2, we know that it's undefined because that's where our vertical asymptote is. Again, we can verify that by typing in 2. And notice we get that error. That's exactly what we expect. Now what about the other side? So 2.1, okay, we're at 13. 2.01, just a little bit closer, 103. And then 2.001, 1003. And then you can probably guess what would come next. Again, now we're increasing without bound. So from this side, we're approaching positive infinity. So on the left of 2, as the x values approach 2 from the left, our y values are going towards negative infinity. As we approach 2 from the right, our y values are going to positive infinity. So because we're approaching 2 different values, our limit does not exist. Okay, and then one final example, same function. What happens as x goes to infinity? Well, let's look at it from the graph first, and then we'll look at the numbers. So as x goes towards infinity, towards positive infinity, trace the graph as x increases. So as x increases, goes towards positive infinity, we continue to approach our horizontal asymptote. Where is that asymptote? Well, it's at y equals 3. So as we go towards positive infinity in that direction, the y values are going to get closer and closer and closer and closer and closer to that horizontal asymptote at y equals 3. So based on the graph, it looks like our limit should have a value for 3. Let's verify that with some numbers though. So we're approaching infinity, x is approaching infinity, so our x values are getting bigger and bigger and bigger. So we want to check increasingly large x values. We'll say 1,000, 10,000, and then 100,000. And honestly, these are just arbitrary values. The idea is we just want to pick numbers that are increasingly large in scale. You wouldn't want to pick 1,000 and then 1,001 and 1,002. The idea is you want to generate what it would look like going towards infinity, getting increasingly large in scale. So when x is 1,000, we are at 3.001. Okay, 10,000, 3.0001. And notice because I've reached the end of the table, it's now just overriding what I'm currently on. That's okay. And then x is 100,000. And technically, we don't actually reach 3. So I'm going to put 3 in parentheses. Your calculator is limited as to what it can do in terms of just evaluating numbers that are really, really big, those kinds of things. So technically we're not quite at 3, we're at 3.000 something, but your calculator is saying it's so close to 3 that you can basically call it 3. So the idea again is, what are we approaching here? Well, we're approaching a value of 3, which again made sense because 3 is where we have our horizontal asymptote, and we're approaching that asymptote as we go out towards positive infinity along the x-axis. So in this case, our limit is going to be 3. So we're going to use limits in a variety of different ways throughout the semester, looking at different topics, different applications of limits, different specific situations within calculus where limits are going to be helpful in helping us define specific things. So in this video, we looked at numerical limits, graphical limits, how we evaluate limits in those using those techniques. Limits can also be evaluated algebraically, just looking at the function we're taking the limit of, and that's what we'll explore in later videos.